Hi everyone, and welcome to this webinar on how to use Alteryx to optimize the route around the Monopoly board. The content for today's session is available from the link that you see on your screen, which is till.bi/Monopoly. It's a case-sensitive link, so just be aware of that if you wish to download the content. Something I will add is the format of today's session is going to follow a roundabout way of I'm going to be acting in this kind of host role. Gwilym is then going to do majority of the talking. He's going to hand back very briefly to me, and then I'm going to hand back to him to close off today's session, which is good because it means I've done a lot less of the work than Gwilym has, so thank you for that. I'll just introduce who I am. So my name is Ben Moss, and I'm an Alteryx and Tableau consultant for the Information Lab. I'm also an Alteryx ace, so I'm recognised by Alteryx as one of the leading users with the platform. So hopefully I can impart some wisdom, but I'm sure Gwilym's going to impart a lot more than I am today. With that, I'll hand over to Gwilym, who's going to take you through 80% of the presentation.
Cheers, Ben. Hi, everybody. I'm Gwilym, and I'm also a consultant at the Information Lab. I'm not an Alteryx ace, but unlike Ben, I haven't done a digital detox, which is why I've got my Twitter handle in here if you want to get in touch there. One other thing to mention is that as we're live on YouTube, we can see the comments in the chat. I know it's not the same as being in person, but it's still pretty good. So if you want to chip in or ask us a question or interact with us and so on, that'd be great. You know, I really miss teaching in person. So yeah, we're looking at the chat, and if you want to say something, like, by all means, please do. All right. What is optimization? First things first, what is it? Optimization is finding the best solution to something, like any kind of problem that you've got, out of all the possible alternatives. And it generally comes with certain constraints. It's probably easiest to describe with a few examples. So let's say you're at a restaurant and you've got a menu with the price of each item and the number of calories in each item as well. If you've got 20 quid to spend, what's the largest number of calories you could consume for that? Well, to solve that problem is pretty straightforward. You just calculate the item with the highest number of calories per pound or per penny or like per unit of money. And then you'd order as many of those as you can for 20 quid and then pad out the rest if there's anything left over with something relatively cheap. On this particular menu, as I've been scanning through, I think that the most calories you could get for 20 quid off this is 6 vegetarian breakfasts and then one of the breakfast wraps. But you know, on most menus, when I've tried to solve this before, when I'm in certain pub chains, the highest calories to price ratio is normally something like paying the extra 10p for extra sachets of mayonnaise. And let's face it, if you wanted to consume as many calories as possible for 20 quid, you probably don't want to just eat 200 sachets of mayonnaise. So let's introduce some constraints. What's the most calories you could consume for 20 quid, where you also have to get at least one breakfast meal, one extra drink, and at least 2 breakfast deals? Now, this now becomes a lot harder to do just by staring at the menu. Another example is fantasy football. So this is my colleague Ian's team, or at least it was a couple of weeks ago when I was putting these slides together. I hope he doesn't still have that 3-man Liverpool defense in anymore. Hopefully he's changed it around before yesterday. But yeah, fantasy football. You've got a budget of 100 million and you have to pick 15 players with at most 3 players from the same club. Now, there's lots of possible solutions to picking your fantasy team here. There's so many different combinations of players that could add up to 100 million. And picking players individually will often end up either maybe a little overspending or underspending, or just not noticing that you've got 4 people from the same team, and then you try and hit submit, and then it tells you that this isn't possible. Now, an optimization strategy would find a solution where you spend the maximum budget, pick the right number of players from each team, and if you've got other stats, you could also optimize for the maximum possible, say, expected goals per 90 per player, or maybe progressive passing stats, or whatever it is in fantasy football that matters most to you, that makes you think that you will have the best possible team. Another type of optimization is the traveling salesperson problem. And this is where you've got a load of different locations to visit, and you want to do it as efficiently as possible. So in this diagram here, we've got 9 different places to visit. We could connect them up like this, which looks like a long and inefficient way of doing it, but it's still an option. Or we could connect them up like this, which looks to me like the most efficient route. I'll be honest, I haven't calculated this one because I drew it in Microsoft Paint. But this feels like a different kind of question from the others, but it's still about optimization. It's about getting the best result, which in this case is trying to get the shortest route. We're trying to minimize the total amount of distance traveled from loads and loads of different options where you've got certain constraints like visiting each place once. Now, this translates into all kinds of different business use cases. For example, maybe you're a medical professional trying to plan home visits efficiently, or you're a retailer delivering packages to different addresses, something like that. Or maybe you've got a stock portfolio where you're trying to find the best balance between the highest possible gains for the lowest possible risk. Or maybe you're planning a budget for your business next year, and you want to find the combination of projects that can be best spread out across your staff and resources so that you're not hitting any bottlenecks, but also spending as much of your budget as possible to make sure that it's used. Now, all these problems are solvable through optimization strategies. And that's what we're going to do today with the London Monopoly board. Now, the route around the board canonically starts at Go in the bottom right-hand corner here. And then we go clockwise through the brown, blue, pink, orange, red, yellow, green, and then I never know whether that's purple or navy or indigo, but that kind of shade. This is roughly in order of value of the property in the areas, or at least the value at the time that the game was designed. But geographically, the route around the board goes all over the place. So we start at Old Kent Road, the only location south of the river. Then we head over the river and out east to Whitechapel Road, then all the way towards the blue squares are in the north bit of central London around King's Cross. Then we veer over towards West London for the pink squares. And then after that is back and forth and round that area of central London in general. And it's just a bit of a mess. Now, if you walk this exact route from Old Kent Road to Whitechapel Road to King's Cross Station and so on until hitting Mayfair, which, by the way, isn't really a street. Like most of these are actual just streets in London, but Mayfair is an area. So for the purposes of this, we kind of picked just a spot in the middle of where Mayfair is. But yeah, if you walk this until you get to Mayfair, it comes out at a little under 60 kilometers. That would take you around 12 and a half hours, which is, probably not the most efficient way of doing it. Now, you can see it visually just by plotting it here. There's so much crisscrossing between all the locations that it's obviously not the most optimal route to take around the locations if you want to keep it to a short distance, or if you want to just achieve it in less than almost a whole day. And this is where I wish we were doing this in person, because I want to take guesses. If the actual Monopoly board route is, let's say, just under 60 kilometers, how low do you reckon we can get the route distance through optimization? I'd love to hear suggestions in the chat. But hopefully you can give us a shout in the comments on the YouTube chat. I can see them on my screen. So if you put some suggestions in the chat, that would be great. But yeah, from a starting point of just under 60 kilometers, just keep that one in mind, because we're going to optimize it to reduce it further and further. It'd be interesting to get an idea of what kind of final distance you guys in the audience reckon is going to be a realistic outcome. And anyway, since this isn't the optimal route, it needs optimizing. How do we bring the route distance down while still visiting each location at least once? Now, one thing we could do is go from south to north. It doesn't really count as an optimization technique per se, but it's one way of bringing it down. We could hit each location in order based on a geographical property rather than the property price. So here we're just hitting each location in order of latitude, going from south to north. This shaves off a couple of kilometers, but obviously it's still not great. Look at how it veers all the way over from east to west. So we could try going from west to east instead. This still has some inefficiencies where the route kind of bounces from north to south, but just taking the locations in order of longitude takes 17 kilometers off the Monopoly board order. So we're down to 40 kilometers, and we can still definitely optimize it further. I spent a while trying to work this out earlier in the summer. So although, to be fair, I cycled it rather than walked it, because that would have taken all day. My approach to optimization was staring at Google Maps and dragging the route planner thing around until, after a while you drag it around and Google tells you that like you've hit the maximum number of adjustments that you can make to the route. Yeah, I was trying to do that, and then I'd maybe start at Old Kent Road and go work backwards and go as far as I could with the before it started before I hit the route the route adjustment max, and then in another tab I'd have the same destination to another place and so on. It was a bit of a mess, but I came up with this route to cycle, and I think it was all right. If we take the order that I chose and plot it with the most efficient walking directions, this isn't too bad. We've taken another 9 kilometers off, and now we've almost halved the initial distance around the board. But if we want to optimize it properly, well, let's talk about some different techniques that aren't just going through by latitude or by longitude or by staring at Google Maps. So one is just a simple brute force search. And this is probably the most intuitive approach. Why not just calculate all the different possible routes, and then once you've done that, identify the best one there is? There's 2 reasons for that, which is maths and computational power. So there's 26 monopoly locations on the board, and it doesn't seem like that many. Like, it feels like that's a manageable number of combinations. But the thing is that even with only 26 locations, that means that the number of possible combinations of them is 26 factorial, or 26 by 25 by 24 by 23, and so on. And that grows like really, really quickly. It's hard to grasp just how quickly adding a single item increases the number of possible combinations, which is why I made this GIF, because it's I can see it in my head up to like, oh, if you've got one thing, you've got one combination. 2 things, 2 combinations. Cool, great. If you've got 3 things, there's 6. There's 4 is 24. 5, 120, and at this point, it's the numbers just blow up in my head to the point where I can't even really compare it. And then you think that, oh, you're only adding 1 extra thing. Like, once you've got 10 combinations, adding 1 more to get like 11, surely that, it multiplies it out a bit, but by that much? Yeah, by that much. It would go from 3.6 million to like, well, I can't do that by 11 in my head, but like around 40 million. The number of combinations grows hugely, which is why 26 factorial, that many combinations, isn't going to work here. And so, the number of possible combinations when we've got 26 locations in the Monopoly board, it is, deep breath, 403 septillion, 291 sextillion, 461 quintillion, 126 quadrillion, and 606 trillion different possible routes. And I did have to write that in words because this is way too many numbers for me to read off the screen. Now, this is just way too much data to be handled by, let's say for no reason, an Excel file. Even if you maybe split it up into many different Excel files, it's still way too much data for it's too much data for billions of Excel files. It's too much data for dedicated databases to handle as well. So brute force search simply isn't possible with this kind of solution. And we'll never know what the absolute perfect route around the Monopoly board is, but we can get close. And one way of doing that is to use the next closest place strategy, which I'm just going to hand over to Ben to explain.
Thank you, Gwilym. Let me just take control and share my screen. So as Gwilym said, when you use the brute force search mechanism, it's not something that's really possible or plausible once you go from even just quite a few number of desired locations to visit. So then you have to think about, okay, what ways can we create an approximation of the best route? And one of those is something known as the nearest neighbor algorithm, or as we put here, the next closest place, because we think that kind of describes the idea a bit better. So what you do is you have all of your locations geographically spread around London. And what you do is you select just a single one of those points. From those points, what you will then do is travel to your next closest point or your nearest neighbor point. So in this case, that's going to be this point here. So we're going to move from our yellow point. They're all yellow points, so that's probably not the best way to describe them. We're going to move from the starting point to our next closest place. From there, we then repeat the same process. So we now move to the next closest point to this point, which I believe just visually, it seems to be quite close either between this one and this one, but if I remember correctly, it is this one up here. So we then do that move and then essentially repeat the process. Now, your brain is probably telling you that this logically makes sense as the next point to go, because then you can go and finish these ones off. But actually, because this one is the next closest point, we're going to go here first. And this repeats itself until you then complete your route. Now, something that's worth noting with the nearest neighbor algorithm and a way to kind of tell if what you're building is a route that makes sense and is likely to be optimized. This is, of course, always going to be somewhat optimized, but it may be there may be cases where you can find much better routes or only just better routes. And one way to tell that you may be able to find much better routes is the general rule where if the end stages of our route, so this final step that we have here, which is really, really long, if that is extremely different to the legs at the start of your route, i.e. in terms of distance, then it's likely that there is a much more optimal route around the board. And that's clearly the case here. So we've got this really long last leg, and we've got shorter ones at the start. So what I'm going to do is just briefly dive into how this translates into an Alteryx workflow. And before we do that, I'm going to just showcase how we get the data required for this analysis. So I've got Alteryx open in front of me, and you'll see that I've got 1, 2, 3, 4, 5 different workflows that I'm going to show you. So let's start with the first one, which is how do we actually generate the data that allows us to perform a task like this? So this is essentially a very brief tutorial on how to create a distance matrix in Alteryx. So what we do is we start with a list of different points that we have or different locations that we want to visit. Now within Alteryx, there's a handy tool called the append fields tool, which allows us to do what is known as a Cartesian join. This will take all points from one side and merge them with all points from another side. And if we plug our input data into both of these sides, you end up with an output containing all of the different combinations of locations. So the first one we have is between Old Kent Road and itself, Old Kent Road. The second one is Old Kent Road to Whitechapel, and then Old Kent Road to King's Cross. And if I scroll down, you'll see we end up with all of those combinations. What we must do, of course, is we can't travel from Old Kent Road to Old Kent Road. That is a pointless journey. So we've just dropped in a filter tool to remove those records. The next step of this process is to actually go and get the distance. Now, there's a few different ways you can do this. One way is to use the tools available with Alteryx and the additional data packages which you can purchase from Alteryx, which would allow you to do this directly in the product. Alternatively, you can make use of a API provider, Google Maps being one, travel time platform, Mapbox. You can name tons of the things. Usually, they're going to involve some cost, but you may be able to get the number of requests you need within a free limit. In this case, I've used a travel time macro, which allows me to go and retrieve the walking distance, as I've specified here, between each of my different paths. I then take the result, and I'm not going to run it now, and that provides me with a data source which can be used for our analysis. So let's move on back into the nearest neighbor algorithm, and I'm going to start by showcasing what the result looks like and then break it down into its different components. So this outer level workflow, the nearest neighbor workflow, contains the result of our algorithm. So we start with our distance matrix. So from Bond Street to Bow Street, it's 1.5 kilometers. Direct distance, or 1.98 kilometers walking distance. What I've done is then used a batch macro to calculate all of the different routes that are possible using this nearest neighbor algorithm. Now, the reason I say all of the different routes is because in the first slide we showed you, we selected just a single arbitrary point on our diagram. What we can do to identify all of those different starting points is just cycle through them all one by one. So that's what I've done here in this batch macro. The batch macro then feeds the looping macro within it, which then actually calculates the route, and I'll dive into that in a second. And what you end up with is a route or a series of routes that look something like this, and all of the different starting points. And if I just quickly sort this, you'll see that the lowest distance route that we can generate using the nearest neighbor method is 26.497 kilometers. So we've shaved around 30 kilometers off the original Monopoly route, and we've shaved around 10 kilometers off Gwilym's cycling route. So Gwilym, we could have saved your legs slightly with that one. So what I'm now going to show you is the actual looping mechanism. So that's the actual thing that's doing the nearest neighbor piece. And quite handily, it's in a macro called nearest neighbor loop. So with this macro, what you must do is feed it with your starting location. So our starting location in this case is set to Old Kent Road. With the bottom anchor, we then have our distance matrix, which you've seen a few times already, so I'm not going to describe it again. We then perform a join to identify all of the possible locations from Old Kent Road 2. So we're going from the destination specified to any number of destinations. What we can then do is a second join, and this makes more sense on the second piece, which then removes any locations that we've already visited. Now at the start, we haven't actually visited any locations, so this join still returns me all of our records. This is where the nearest neighbor piece then comes in. We've got a sort tool where we have sort by walking distance in ascending order. So returning me the lowest value first. So the closest station to Old Kent Road is Fenchurch Street. And then we use the sample tool to take that as our first leg in our journey. So our first leg is Old Kent Road to Fenchurch Street. Now, what I will say is in our distance matrix, we see other values which we might actually want to sort by. Perhaps walking distance isn't necessarily what's important to you. Perhaps walking time is, because you'd rather do it quicker, regardless if it's a slightly longer route. In that case, all you would do is change what you sort on. So we could just change this to walking time, and the algorithm would adjust accordingly. So you don't have to build your traveling salesman problem by distance. It can be by any metric that you have. Miles per gallon might be another one as well. So we've sampled the result, and then we move over to this final part of the macro, which I'm going to describe in two parts. So the bottom bit is where we store this leg of the journey. So I've added my leg number as a field to the right side of my file. So this is leg number 1. At the top, what I'm doing is essentially telling Alteryx whether it needs to run this loop process again. Of course, because we've still got destinations to visit, we do need to run this looping process again. So we are passing our locations back to the start, but this time our locations list isn't just Old Kent Road, it's now also Fenchurch Street. And this is where we then come to the second iteration. So we're now repeating that process, but for a second, or for the second leg of our journey. So now we have Fenchurch Street and Old Kent Road. We take our top record, which is the latest place we've visited, so Fenchurch Street. We then perform the join to identify from Fenchurch Street all of the distance to the other locations on our Monopoly board. And then we use our second join to remove Old Kent Road from that list. That's because we've already been there. The purpose of the traveling salesman problem is to not travel to the same place twice. We then perform the sort and the sample to essentially create our second leg. So our second leg is Fenchurch Street to Liverpool Street. And then we move through the process of storing that second leg of the journey and outputting that list of visited destinations. And this is going to keep expanding. And the way this macro has been built is that eventually when all locations have been visited, this condition here will fail. The count does not equal 0. So that count is the number of destinations left. So that's how the nearest neighbor mechanism can be built in Alteryx. So it's using an iterative macro. So an iterative macro allows you to form looping processes or while loops. But what I'd recommend is, and this is one reason why we make the materials available, if you truly want to understand how this macro works, dive into it and look at it yourself. So please download the materials that that we nudged at the start of the session and will continue to nudge throughout. We then have the batch macro process, which is designed to essentially repeat this for the different starting locations. And with that, I'm going to hand back to Gwilym, who's going to take you through another algorithm that allows you to potentially bring down the distance further.
Cheers, Ben. Hopefully you're seeing the screen with the next closest place, or we see that
I am Gwilym. Just
yeah. Yeah, so this is like just a visual summary of the one that the next closest place algorithm found, and yeah, we're down to 26.5k. This is an improvement of about 5 kilometers on my like pointing at Google Maps and trying to figure it out. So this is we are making progress. Now, another way of optimizing this route search is using genetic algorithms. These sound pretty complicated, and they can be at times, but the general mechanism of how they work is like relatively straightforward. So let's say we've got again a nice simple map of locations. I'm only drawing 6 this time because Microsoft Paint can get a bit tricky. So we've got the locations, and again I've mapped out the distances between them all, and this is definitely totally accurate again. And yeah, I want to find the shortest route that will take me through all 6 locations. With the genetic algorithm, you can start out by building a collection of possible routes called a population, and then that population evolves by finding which of the possible routes are the best and then breeds them together. At some point, the route distance stops improving, or it's improved so minimally that it doesn't really make much difference, and you get a final route. It works a bit like this. Each location on the map is a gene, and the genes are combined to make a chromosome of different genes, which is the route. If we get a few different chromosomes, say a few hundred instead of a few hundred septillion, we can put those chromosomes through breeding and mutation over several generations. So in this example here, I'm starting out with a population of 3 chromosomes. These are my 3 routes around the different locations. Yeah. But what we're going to do is, of those populations, find the distance for each of them, select the best ones, discard the less good ones, and keep them on for another generation. So yeah, we select the 2 best chromosomes and discard the worst. So in this population of 3 chromosomes, the top root and the bottom root add up to distances of 66 and 68, which isn't too bad. But then the middle root, that adds up to a total distance of 92, which is kind of rubbish. So let's discard that one and just keep the best ones for the next generation. Now we've got 2 parent chromosomes and we're going to breed them. That means we'll take a random part of one parent and splice it together with the genes from the other parent. So here, let's take genes C and D in positions 3 and 4 from the first parent. So the child chromosome is going to inherit those two genes in those positions. And then from the second parent, we can fill out the remaining genes in order. So now we've got a brand new route which combines aspects of some of the best solutions that we found. Now, the idea is that over several generations, keeping the routes that add up to the shortest distances and mixing them together like this will create routes which are shorter still. Now, of course, it can also create routes that are longer as well, but that's why we have the selection procedure at the end of each generation to get them out of the gene pool and just keep the shorter ones. We can also introduce a bit of mutation across generations. So here we've got another chromosome. It's identical to the chromosome in the first generation that simply went A, B, C, D, E, F. But this time it's undergone a natural mutation where two genes have just swapped places. This introduces variety into the population, and sometimes it'll make distances longer, but sometimes it'll actually improve things and make distances shorter as well. So this is how the mutation aspect works. Now, if we add up the distances for these chromosomes in the second generation, we can see that the distance of both routes has decreased to 57. Now, this is progress, which is great. And the idea is that doing this over multiple generations will eventually bring down the distance to a number where it can't really evolve much further. Now, that doesn't mean that we've found the absolute shortest possible distance between all points, but it is a pretty efficient way of getting pretty close. Now, luckily, there are lots of tutorials on genetic algorithms online. And for the monopoly route one, I used this really, really useful blog by Eric Stoltz. I adapted some of the Python code and I just put it into the Python tool in Alteryx, which I will show you now. So this is the genetic algorithm workflow that I've got. It takes a little while to run, and you can change the settings depending on what you want it to do. So we start with the distance matrix that Ben created in the last one. So we can see the points, the starting points, the finishing points, and the walking distance between them. Just do a little bit of preparation. We sort it in like ascending order, both from and to. And this tool, well, the code in this tool needs two different inputs. So one of the matrix of distances and one of just a nice simple list of the different locations. This one may take a little while to load. The Python tool is really useful, but it's because it's got these like Jupyter notebooks embedded into it. It takes a little while to load. So while it does that, I'll briefly explain what it does. There is a lot of code in here. It doesn't need any specialist packages that don't already exist in the Alteryx download, at least for 20.3. But it does require a lot of custom functions. So what we do here, I'm not going to go through everything at all because there's a lot. But just to give you a brief overview, we bring in the two different data frames. So that this one at the top, just here. Number one, we just bring in the data frame of values, with the walking distance and walking time. Just create a new variable, which is just the same two, the from destination and the to destination concatenated together, and we save it as a list. Then in data frame 2, this is the simple individual list. We just bring that in as a simple list of 26 places, which we can double check just here. Now within then we need to create a lot of custom functions and definitions and classes and so on. The main one for establishing what the route distance is this bit here. It's basically just not in a way not dissimilar from the iterative part of Ben's macro, but what it's looking at is it's going through a route or like generating a random route and going through and finding the distance between each place and bringing that in and then summing it all up. And this is the bit that gives us the total route distance every time the generation is run through. Then we've got a lot of different things. We've got the thing that creates the random routes of the different places with the number of places that there are. We've got the defining the initial population, the it ranks them, it does the selection procedure, we've got the mating pool to kind of breed the parents, then we've got the actual breed function, then it brings through the breed population, we've got some mutations going on here, it then mutates the population to a certain proportion of it, takes it through to the next generation, and then overall, the final function is to apply this genetic algorithm, which takes all of these different parameters. And the bit that does the magic is this bit of code here. What this is saying is that with all the functions that we've defined earlier, do a genetic algorithm, please. Start out with the population of the list of places that we want to go through. We want 200, a population size of 200, which is like 200 different routes created at random to begin with. The elite size, that's what we take through to the next generation. So from each generation, we'll have like 200 things, bring through the top 20, and then to 1% of them, just put like a random mutation in, and then do that for 800 generations. That starts out with the initial distance. This is of all the ones that of all the random routes that we start out with, the shortest one is 60. And over 800 generations, we get to the shortest final distance of 26.287. This isn't too bad. And this algorithm runs in about 2 minutes. Now, the thing with genetic algorithms is if you want to increase if you want to get a potentially better result, you can increase the population size, because, the more random routes you start off with, the more chance you have of having a particularly good one in there, and then take the good ones and so on. Maybe the more generations that you add in as well, the more likely you are the longer that you give it to evolve and throw up new mutations and throw up maybe better combinations. But it will also take much, much longer to run. So this is where it becomes a trade-off between how long you want your process to take and how long, how quickly you want a decent answer and how accurate you want the final distance to be. I found that this is also a really nice bit of a really nice example of the most fun parts and the most frustrating parts of coding was when my whole algorithm procedure was taking about 2 hours, which was forever. And then I realized that I could make this hundreds of times more efficient by I realized I still had a data frame, a Python data frame in the middle of a loop, and data frames are just a lot slower to process than lists. So I just converted the thing to a list instead of a data frame in the middle of the most internal for loop. And the thing that used to take like 2 hours then took like something like 10 minutes, which is it was really satisfying, but so frustrating at the same time. But yeah, this was really nice to play around with. The vast majority of this code comes from that blog from Eric Stoltz. It's on Towards Data Science. Cannot recommend it enough. Much of this is just copy pasted and then adapted slightly to fit the monopoly route's specific quirks. And yeah, what we did was run this a few different times with a few different settings. And the best genetic algorithm the best result from the genetic algorithm that I got was 25.9 kilometers, which is pretty good. Like a lot of them hovered around the 27K. We saw in the one that I ran previously that was in preparation for this, it was 26 point something. Was it 26.8, 26.2? But yeah, some of them broke the 26K barrier as well, which takes a whole 600 meters off the next closest approach. This route here is walkable in about 5.5 hours, which is nice. But there's a final twist to the tale with the genetic algorithms and the optimization. So our best route is a really satisfying illustration that there's still a place for the human eye and analysis alongside complicated algorithms. So the best route we found overall was when we took one of the genetic algorithm suggestions that was about 26K, plotted it on a map, and we saw that the suggested route took a couple of weird detours. So instead of this, which adds up to 23.2K, it would do something like it did the exact same route, and then instead of going from here to here to here to here, or vice versa, it went something like from here to it went something like from here to here to here to here to here, here to here, and so on. And it was just obvious from the map that this was like, you could shave distance off that. So we just simply switched those locations around, left everything else the same, and ended up with a 25.3K route that would take just under 5.5 hours to walk. But the interesting thing about optimization is it's possible that there's even shorter routes between all the Monopoly board locations that we haven't found yet, and possibly this may well be the shortest. Just looking at it visually, I can't see a way of improving it, and I have tried. I was wondering if we could go from in this green one here. I was wondering if we could do instead, say, go from here to here to here to here to here or something, and I tried it, and that way is actually longer. But yeah, it's still possible. There's a combination that is shorter. So maybe I'd find it if I run the genetic algorithm for thousands of generations with 20,000, an initial population of 20,000, with, and then maybe play around with the mutation rate, bring in more. The downside is that if you play around with the mutation rate, most mutations will probably make things longer, or like introduce more distance. So it's possible that you've got a really nice set of chromosomes that are breeding and splicing and getting like much smaller, and then because you've set the mutation rate too high, you're getting really close to a good solution that'll be like there in about another 5 generations, and then you just mutated it to do something really silly with it. So you've got to play around with it as well. But yeah, maybe I'd find a better solution if I just have a bigger population and more generations and set it running overnight without like blowing my laptop up. It's possible. So yeah, if you want to download our workflows and have a go yourselves, please do. So you can find them at till.bi/monopoly. And yeah, please do let us know if you find an even shorter route. That'd be really interesting. But for now, it looks like the shortest route that we found is just over 25K. And I'm going to go back to the live stream for a moment because someone, Oiku, was saying, yeah, maybe we could optimize it to 20. Yeah, sadly, we didn't get quite that short. But yeah, bringing it down from nearly 60K with the Monopoly route to just over 25K, that's a huge amount of optimization. We've more than halved the route, which is pretty good for a business context if you're trying to save fuel and time and money. And yeah, otherwise that's everything from us. So thanks a lot for joining. I hope you found that it's useful, and I hope that you've enjoyed following along as much as we enjoyed creating the materials and doing the analysis. And yeah, if you want to walk around the whole London Monopoly board, well, now you know that you need to leave about 5.5 hours for it and start either at Old Kent Road or the Angel Islington and walk and loop yourself around. So yeah, this is us again. Names and Twitter handles if you fancy giving us a follow. If you've got any questions, just Google us and get in touch on LinkedIn or through the Information Lab emails, which you can find on our site. I'm pretty easy to find with my name. It's quite unique. And Ben is such a star that if you just search for Ben Moss Alteryx, you'll get him. You'll get him. And yeah, otherwise we're always happy to help. Ben, do you have any last words, final words, criticisms of genetic algorithms, or criticisms of taking the outputs of algorithms and just kind of tweaking it a bit?
I mean, the 300 or 600 meters distance you saved was well worth it. But as you say, like in a business context, this is actually quite valuable when you think of the starting route that we had and how far we've trimmed it down. And of course, most businesses operate nationally, so as the distances get larger, then your savings will get larger too.
Yeah, and even shaving off something as like it feels as minor as 600 meters. It's when you're doing that at scale, like if for some reason you've got hundreds of people driving these routes every day, like if you're something like TFL or maybe a taxi hire company or something, that's going to really build up in your costs.
It will. The only thing I will say to finish off is that there is a blog post which is essentially the content of this YouTube session. So if you prefer things written down, which I know a lot of people will, then that blog post is available on the Alteryx community. And I will also drop a link into the YouTube chat now for people to reference. But otherwise, thank you for joining today's session. Thank you to Gwilym for doing most of the work. But with that, we'll close off the live stream. So thank you very much.
Cheers, everyone.